back. I hope you're having a good time at the Innovate conference today. This is an online conference that AWS is hosting. Now, this is my third presentation, and I've been trying to do this in every single time zone, and we're not going to go for the full hour. I'm tired. It's been a very long series of presentations, but I still want to give the people who are checking out the conference in this time zone the chance to review the materials that we built in the previous two sessions. So in the previous two sessions, we built a Twitter bot. Now this bot is live on Twitter now. It's twitter.com/whereml, and you can go play with it. What you do is you post a picture, and it tries to guess where in the world that picture was taken. And I'll cover the various components that surround how this works briefly in this presentation, and then we'll go to some of the code and talk about that. As for myself, I am just I'm a regular software engineer here at AWS. I build a bunch of demos, and almost everything we're going to be doing today is going to be in Python. And you can find most of the code for this over on GitHub, and you can find a bunch of the blogs that I write over on the AWS blog. So if you want to see this in action, you can see it right here. So you can take a picture of your screen right now, and you should be able to get a picture of, or you should be able to go to the whereml bot on Twitter, and it should run just fine. And as you can see, I'm posting a photo, and that photo runs, blah, 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 blah. We get our result, which is a Google static maps image, and it says very confidently this was taken in Seattle. So if we look at the architecture here, we're relying on a feature of Twitter, an API in Twitter, which is their webhooks API, specifically their account activity API. So that account activity API, you register a webhook, which is in this case an HTTPS endpoint that's hosted by API Gateway. That HTTPS endpoint will invoke a Lambda function. That Lambda function will read the payload that was sent by Twitter to the API Gateway, and it will call out to Amazon SageMaker with the URL of the image that was contained in the Twitter bot. That SageMaker stuff we can talk about at length in just a little bit, and this ECR stuff you don't need to worry about. Essentially what happens is it gets an inference from SageMaker about where in the world that image could be located, calls back to Twitter, and tells Twitter to post the image with a bunch of cool stuff in it. Zader asks if I can increase my voice volume. Not really, no. I can speak louder if that helps. Sorry about that. I could get closer to my microphone here. Sorry. If I turn up the volume too much, it will the gain, you'll hear the fan noise. It won't be ideal. So let's take a quick step back and talk about artificial intelligence. Artificial intelligence is really not that new. We've been doing stuff with AI for probably 60 years now. The advantage and the reason you're seeing ML and AI pop up so often now is that we're at a point where the hardware is really able to make up for some of our bad math, because our math is pretty bad. And we're kind of coasting right now on this really, really nice hardware, this really cool GPU-powered wave of deep learning stuff. And it's allowing us to make some of the math better. And so it's this positive feedback loop where we're starting to see a lot more uptake. That said, Amazon has been doing AI for probably 20 plus years. So if you remember, when you buy something on Amazon, it'll say, people who like this also bought this. Is this a product that you would like too? And it uses an algorithm. Well, I mean, it doesn't use this anymore, but originally it uses a simple algorithm called SVD to try and determine which kind of different populations wanted that same sort of thing. So our mission with ML at AWS is really to kind of put machine learning into the hands of every single developer and data scientist. And if you don't believe that, I'd like to just share a brief anecdote. So there was a recent advance in a very difficult mathematical problem about coloring infinite graphs, and the way that advance was made, it was made by a hobbyist. It wasn't made by a full-time mathematician or by someone whose job it was to do math. It was made by a hobbyist, someone who spun up an EC2 instance and was playing around and was able to solve this kind of 800-year-old problem about the coloring of infinite graphs, and was able to come up with a bunch of different geometrical arrangements for that problem. So when you put ML into the hands of as many people as possible, instead of having it kind of siloed and locked into these Fortune 10, Fortune 100 companies, you are really doubling the chances or dramatically increasing the chances that someone's going to bring a unique perspective to bear on a complex problem and hopefully solve it. So that's kind of what we're doing today with this online conference, is we're kind of hoping to put machine learning into the hands of more people. That said, there are a couple different layers of AI at Amazon. So at the core layer is the infrastructure side. So these are the kind of EC2 instance types, the things like the P3 and the P2, and they provide the core underlying infrastructure for all of the other services that take advantage of ML and AI. Then you have your platform services, things like SageMaker, which is what I'll be talking about today. And then even beyond SageMaker, you have simple APIs that you can call out to, things like comprehend, recognition, and others. Now, lots of different customers using AI on AWS. And yes, Bill Shinzi asks, I have a question. Absolutely. Oh, are you making fun of something I said on Twitter earlier? I absolutely recommend asking any questions. Please, this is an interactive session. I am in a presentation right now, but we're going to hop over into some code in just a little bit. So any questions you guys have, I feel free to interrupt me. I will do my best. And then Chow asks, how do you define your activation function? So activation functions, we should cover that. So let's take a quick look at this video. So the way that typical neural networks are talked about is you have a set of neurons, and these are really modeled after the visual cortex of the human brain in many cases. What I mean by that is, let's imagine a scenario where I'm looking at this screen, right? And the light that's being emitted from these screens is going into my eye, it's going through my lens, and it's hitting the retina. The retina is connected to the optic nerve, and it's generating an electrical impulse that's going into my brain, and it's triggering a section of my brain called the visual cortex that's coalescing the information coming in over my eyes into context and into conscious thought. So the way that those neurons are trained is we learn by sort of trial and error, and we learn by pattern matching and association. And so when we create these networks, what we're really doing is we're trying to teach them in the same way that we kind of model the visual cortex. Now, whether that's an exact representation or not is something that could be argued, and I'm not a expert in biology, so I wouldn't be able to make that argument. But I will say that this model has served us quite well, and we're able to build kind of complex networks on this very simple structure. So what we mean when we talk about activation functions and biases is, let's imagine a scenario where we're taking 28 pixel by 28 pixel handwritten digits. There's a really common data set called the MNIST data set. It's a set of handwritten digits, 28 pixels by 28 pixels in grayscale. You may have seen this in Julian Simone's presentation earlier today. And what happens is we can take those 28 pixels by 28 pixels, flatten them into one layer, and treat each one as a input node. And it's either, it can have a value between 0 and 1 or 0 and however many bits you want to use to represent your grayscale image. And then we can connect it with a second layer that hones down into a smaller set of things. We could have yet another layer. So this would be a fully connected layer. I'll skip ahead a little bit here. So this would be a fully connected layer in which every neuron is connected to every other neuron. And then we would have another fully connected layer followed by an output layer. And that output layer is really just the digits 0 through 9. So what we're trying to do in that output layer is we're trying to say, hey, I have all this stuff. I want you to try and figure out how to classify all of this. So when we talk about training, what we're trying to say is given the 784 input matrix or array, I want you to tell me what is it most likely to correspond to in this output array. And what happens in between is not really something that we always have to care about when we're designing this stuff. Or sorry, when we're using this stuff. When we're designing it, the stuff in the middle is very important. So if you think about it, what training is you initialize all of this stuff with random values, and you're just trying to find the right weights and biases for all of these different connections. So let me see if there are any questions that have come into the stream so far. So let's see. So Tony, I'm sorry about the audio. I'm speaking as loud as I can, and on my side things are pretty loud. So maybe try turning up the volume a bit on your side. I can boost it just a bit, but if I boost it too much, you'll just hear my computer fans running. So I just boosted it just a little bit more. Let me see if I can do just a little bit more. Okay, hopefully that's not too loud for people. So in the end, and then Chuck says, if you flatten it, don't you lose dimensional data? Da, 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 da. Well, sort of. So they're different ways of flattening the data, right? In some perspectives, if you know that the input image is of a shape 28 by 28, it doesn't really matter if you're flattening it, because you know what the input layer is going to look like. So then the person who's calling the model is responsible for making sure that it's flattened in the right way. The network doesn't actually care about the shape of it, because at some point it's going to be dealing with an array no matter what. So the network doesn't care, it just sees numbers. There are different ways of designing this network. This is a very simple network. This is not a complex network. There are convolutional neural networks where you actually do multi-dimensional transforms, and those you're kind of like moving a kernel around the image and trying to find edges and stuff. Now, let's just see what this looks like in practice. So basically, we have these neurons, and these are not just things that hold a number. And we're taking that data, and we're basically abstracting. We're as you just saw, we're kind of taking this number 8. We're taking all the pixels, and we're kind of activating it. And you can see a bunch of neurons in this first layer light up, a bunch of neurons in the second layer light up, and we go to this last layer. And this last layer is our output layer. And let's say instead of getting a number 8, we got a number 1 or a number 5. So the way that we would train the network is we would take the loss, the error between that number 1 and that number 9, and say, hey, we've got to propagate this backwards and adjust the weights and biases as we go along in order to get back towards a number 9. And that's where those activation functions come in. And there are a lot of really common activation functions, things like tanh or sigmoid is the oldest one. No one really uses that anymore. You have, let's see, just a whole slew of different activation functions that have different properties and stuff like that. And now maybe your intuition is telling you that what this is doing is maybe this first layer is identifying that, okay, well, I know a number 9 has a bunch of different edges, so these neurons are lighting up to activate these edges. And then the second layer, maybe it is learning that, well, these edges together make a long squiggly piece, so I'm going to activate that neuron. And then I know that I need a little loop. And if that little loop neuron is activated, then I know that it's probably a 9 because it's a combination of a little line and a loop. And there's a question of whether or not the network actually does this. Now, in the case of a simple network like this, the answer is most likely yes. It is probably learning these features in this way. Google has actually come up with a series of tools, or Google researchers have come up with a series of tools that make it really easy to visualize in simple networks what exactly is happening. As you get into more complex networks, things with many, many more layers, the answer becomes much more difficult. Is it actually learning these things? And the answer is no. In many cases, it's picking up on things that we as humans would never really understand or pick up from. And Artist Passion asked, is this from 3 Blue 1 Brown? Yes, all of these animations are from somebody named Grant Sanderson, 3 Blue 1 Brown, and we happily sponsor his work. So you should check out his YouTube channel. I posted a link to it in the previous stream. I'll post another link to it at the end of the day here. And this is, if you are trying to learn machine learning at all, I strongly recommend 3 Blue 1 Brown's channel. Grant Sanderson has probably one of the best grasps of teaching and animation and making complex topics accessible in a very succinct way. So rather than spending hundreds of hours on reading through complex books and algorithms and trying to learn a bunch of new calculus and notation, then you should definitely check out his channel. And I mean, I'll just bring it up briefly now, and I'll post the link because I know that 3 Blue 1 Brown. I know that moderators aren't able to post the links. So let's see here. There's a playlist called Neural Networks. Sorry, my microphone is in the way, so I can't quite see it. So I'm just going to paste this link. If you are interested in learning stuff, Grant Sanderson, 3 Blue 1 Brown is awesome. And Vibi, unfortunately, if you're not a moderator, you're not going to be able to post a link just to prevent a lot of spam. So my network is still training here, so I'm going to hop back into my presentation. So we've talked now about how basic neural networks work. So let's talk about the process for machine learning. And I'm just going to skip ahead kind of towards the end of this process here. The problem that we're facing today is that we want to identify where in the world the picture was taken without having to use and load in all the EXIF data for these images, or maybe the EXIF data is not available. So what we do is first we frame that problem. That is the question we are trying to solve. Now we have to collect the data. The data that we're using in this case is the Berkeley Multimedia Commons dataset. This is available as one of the public datasets on Amazon. It's a collection of 100 million different images. And some people were asking who I am, so I'll just put up my image again. Now, the 100 million different images, only about 34 million of those are geotagged. So only about 34 million of those images have EXIF data. So the next step after we collect those 34 million images and kind of get them into a place where we can start doing stuff with them is to integrate that data and prepare it and clean it. Now, in order to build the first classification layer, we don't actually need the image data. All we really need is that EXIF data, the collection of latitude and longitude coordinates for our training data set. And the way that we do that is we basically just run EXIF tool in a whole bunch of threads across a couple different instances, and we say, hey, grab all this data. And then we use Google's S2 spherical geometry library in order to plot a bunch of indexes. And I'll show you what that looks like in a moment. And it's really important at this stage of the ML process to kind of visualize your results. So look at the clusters of data. Maybe you can even run some simpler algorithms, things like PCA or k-means clustering, to get some idea of like how your data is distributed and what features are really contributing to those distributions. Then after you have some kind of intuition about what the data contains and what you're doing, you get into feature engineering. And feature engineering is really just kind of providing hints for the various algorithms you're going to be invoking later, or surfacing the stuff that matters and removing some of the stuff that doesn't matter. You have to be careful here though, because oftentimes as humans, we don't recognize features that could matter, that could have some impact on the end result. And if you've seen the famous XKCD, correlation is not the same as causation. In machine learning, correlation and causation are a lot more blurry than they are in pure statistics. So then you train the model, and I'll talk a little bit about training the model in a little bit, and then you evaluate the model. And after you've evaluated the model, you typically what you do is you take aside 10 or 20% of the data that you've never pushed through this neural network, and you take that 10 or 20% and you verify that the results are what you expected. And then you say, are my business goals met? And if the answer is yes, then you go deploy it to production. If the answer is no, you just iterate through these other steps over the course of the time that you have. The deployment section of this is what SageMaker makes really, really easy. So I'm going to skip ahead again I'm going to skip past all the marketing stuff, and we'll just go right to the Twitter side of things. Or we'll go right to the discussion of the model. I'm going to check to see if there are any questions. Any questions here? All right. Well, thank you guys for being engaged. I promise we're going to get to some code in a little bit. So let's take a look at the model. The way that the model works is, and I need to fully disclose, this was not my design. I've pretty dramatically modified it and rewritten a lot of the code at this point, but this was never my idea. I am not even remotely smart enough to come up with this kind of stuff. So what happened here is Jae-Young Choi and I think it was Kevin Lee from the International Computer Science Institute in the University of California, Berkeley. They took a paper called Planet by Wayland, who and a couple of others who are some researchers at Google, and they looked at the resulting model and they said, hey, we could probably do this better if we thought about the underlying problem that we're trying to solve. So the Planet paper, what they did was they took a very similar approach to what I've described so far today, except they had an error in several places. First of all, they were using regular floating point numbers for their latitude and longitude, and latitude and longitude, the specificity on that number is important. And the downside of floating points are that they don't represent every number between 0 and 1. It's not possible. In fact, they represent a finite number. So this is based on the IEEE floating point standard, and so you lose a lot of fidelity in your data when you assume that things are floating point when they are not, because floating point is not meant for this kind of statistical analysis. You have to use a different kind of real number representation. So just switching that around gave a significant accuracy increase. And they also used a model called DenseNet, and the resulting or a model architecture called DenseNet. Now, the resulting model that they used to draw their inferences from was on the order of 20 gigs, which is quite large, quite hard to fit into RAM if you were to be running inferences. For instance, at 20 gigs, you would never be able to fit this in a Lambda function, and you would never be able to fit this on a smaller instance. You would have to run a fairly beefy server in order to get inferences in real time. So the researchers at Berkeley, they took that same input data set, or actually a completely different input data set. Google used the Google Images data set, and the LocationNet folks used the Berkeley Multimedia Commons data set. This is a public data set, by the way. You can go and download it and do stuff with it as much as you want. And they took the ResNet 101 architecture. The ResNet architecture is an architecture that was originally proposed by Microsoft Research back in 2015, I think, and it won the competition for image classification. And what they realized was, as you add more and more layers into these deep neural networks, you suffer from a problem of a vanishing gradient, where the errors in your output layer, or sorry, the difference between your desired result and your actual result, the error function that you use to calculate that, it is harder and harder to propagate that backwards through all the different layers of the network as you add more layers to the network. So basically, as you add more layers of abstraction from the original input data, you start to have a harder time. You need more and more and more and more data in order to get everything to propagate backwards. So what ResNet does is it has kind of a cheat code built in. And that cheat code basically says, if I have and this is very hand wavy, it's admittedly quite a bit more complex than this, so if anybody wants to correct me, feel free. What it does is it basically says, hey, if any particular signal is strong enough, I want you to cut over, and go down into my my next layer. And so let me show you what this looks like. And I know this is gonna, everyone completely understands what's happening here, right? So you see TANH and ReLU and all these different activation functions. This is what the model is. And if someone had ever showed me this as like the first ever if someone had shown me what this was as the first ever intro to machine learning, I probably would have quit right then. FGUID says, are the slides going to be available? Absolutely. They're actually already posted. I'll include those now. Or I'll post them later, I guess, because it's not in my clipboard history. And LXXII asks, P2 16x large running over 9 days is $3,000. Luckily, we provided those researchers with credits, but also the spot instances are pretty good. I'll talk about some advances that we've made since the original research published back in 2016. And this is what that S2 spherical geometry library that allows us to do with the spherical partitioning. We use something called a Hilbert curve in order to basically plot all of this and choose the dense layer. And then Spongy Terracer asks, so you feed your data into the network, make a graph, and then use a data modeling tool to convert your graph to those activation functions? No, I would say you... So in this particular case, we're relying on an architecture that already existed. So the topology of that graph was provided for us. The topology of that graph was actually designed for a problem of image classification. So puppy, goat, bicycle, Justin Bieber. It was basically designed to identify differences in things. Now, the activation function portion of this is really just saying, what value do I need on the result of this function in order to trigger this edge to execute, is the best way that I could think of. And then you have biases as well that are put next to that activation function, so that the combination of the activation function and the bias are able to be adjusted, and it's really just the biases that you're changing. You know, once you've decided on the activation function, you're not really changing any of you're not changing between TANH and ReLU and stuff like that, although you can, or over to sigmoid. You're really just saying, I want to adjust all these weights and stuff. And then what we did in this particular case is, you see these cells, these geographical cells here, we took out the last layer of that resonant architecture and we replaced it with these 15,000 cells. That is basically how the network is working. And there's some pros and cons to this approach, but I think everyone is ready to hear how exactly this works. So we are going to take a look now at my completely frozen computer. That's not good. This is why you don't train a like several gig data set locally. Okay, there we go. No. Oh boy, this is not going to end well. Okay, so let's just go over to Vim. So let's look at the stuff that we have already created in the previous labs, or the previous conversations today. So that's not right. I want to look at predict.py. We're going to focus on the machine learning side of this. And then AJ0X asks, so it's similar to how you'd work with the CFAR 10 data set? Yeah, it's fairly similar. And then Artist Passion is very wrong, but you know, I guess you're entitled to your opinion on any other stream. So what we do is we import MXNet, and we basically, SageMaker, which is the service that we use to host this, will basically say, I'm going to populate these environment variables, model path and model name, with the relevant values. So if I go over here to models, I'm glad this is working now. I'm going to close this down. If I go over here to this model, you can see that there's this kind of Docker container that has my model in it. And I think there's probably a training job too somewhere. But sorry, my microphone is in the way of my screen, so I can't really see what I need to see. But oh well. So essentially, we have this this Docker container, and it's going to contain the following Python file. And so there are a couple different ways of doing this. The model artifacts are always going to be stored on S3, and then when we instantiate sorry, I just have to ban somebody really fast. And when we instantiate the tools, sorry, when we instantiate the programmatic invocation endpoint, the SageMaker endpoint, the inference endpoint, it's going to load that model onto the instance for me. So the way that this works is we basically say mx model load checkpoint. We want to load in the 12th epoch, and then we want to bind that module or bind that model to the CPU. Now, there's really no reason to use a GPU in this case, because while we could use a GPU for training, the cost of sending one image over to the GPU, and then kind of, so it comes in over the network, it goes to RAM, and then it goes into the GPU unless you have SNI bypass. Oh, sorry, C-Chalk, you got banned. But you are unbanned now. Oh, I need to unban somebody else too, sorry. The cost of sending all that information over to the GPU is higher than the cost of just processing it on the CPU, the time. So then we set the parameters, and these are just the parameters that we've loaded from the JSON files that were available over here in the model. And then we mean the image, and meaning the image is basically saying, hey, across my entire data set, I wanted to calculate the average colors, and COBOL programmers are more than welcome here. You can join in as much as you want. The reason we mean the image is it helps get rid of outliers, and this is almost, you could almost consider this feature engineering in some way, because what we're saying is stuff that's coming from the dead of night shouldn't all be a strong signal for Russia or something, I don't know. And stuff that's really bright and sunny shouldn't be a strong symbol for Los Angeles, because the weather is going to vary. So we want to kind of mean the images a bit, and that's just one thing. You do that. You mean the images for a number of different reasons that help with image classification. So next we open that grids file, and that grids file is just the where is the PowerPoint? That grids file is just that series of cells that we talked about earlier, and then we do some pre-processing. And if you look at the image data here, when we do the pre-processing, we're basically just cropping to 224 pixels by 224 pixels, which is what the ResNet architecture is expecting as input. And then we go and we subtract the mean from the image, and then we take that normalized image and we return it, and that's kind of our pre-processing step. Now we go on to the prediction step, and the prediction step is really, really easy. Basically, we just create a batch of a single image, and we call mod.forward. So that's saying forward propagate the following batch. And then we take the result, and the result is actually a probability ranking of all 15,527 cells that are output from the model. And what we do is we go and we sort that by the amount of data that, by the probability. Sorry, I am running on just like very little sleep. This is my third session in less than 24 hours, so I'm speaking over myself here. So we take the probability of the result from those 15,000 layers, we sort by that, and then we return the ones with the highest probability. And this is just some helpful stuff for enriching the data. Now, when we get over into the Twitter side of things, we need to go over into Lambda. And Praveen asks, when is the Twitter bot coming up? We are getting into that now. So, on the Twitter bot side, we have the following kind of setup. I have to close one of these tabs just because it's taking absolutely all of the processing power on my computer to stream the logs from this training job. Blatimus asks if I'm doing more sessions later. No, definitely not today. I am going on a 2-day vacation starting immediately after this session. So I'd strongly recommend checking out the video on demand section of the Twitch channel. We have all of the previous sessions there. And if you go on YouTube, we actually have a series of machine learning videos where you have someone who's way more of an expert than me teaching me about machine learning, and it's kind of interesting. And this code is actually already posted somewhere. We built this in a session a year or so ago, and I let Twitch name it, and that was a mistake. The code is actually stored here. Body, make bot face. So don't let Twitch name things is something that I've kind of come up with. And what we're gonna do here is walk through how you make the Twitter webhook section of this work. So first, we're going to load in our credentials, and these credentials are going to be stored in AWS Secrets Manager. And this is really straightforward. It's just going to contain our consumer secret and our access token and all this other good stuff. So the next thing that we do is we calculate the HMAC of the incoming request. If it's a GET request, let's look at the Twitter API really fast. So I'm going to go to dev.twitter.com. Yeah, boy Kizzle, the worst part of one of my streams was I had transposed the Y and the N in DynamoDB. So for 2.5 hours, I sat there wondering what on earth I had done wrong, what on earth I had ever done to deserve the insanity that I was currently experiencing, and I had just misspelled DynamoDB, and it took me that long to figure it out. So let's look at the account activity API, which is what we're going to be using today. And what this allows you to do is it provides a webhook. So you go in and you have a little fancy video now. This is nice. When I first started using the account activity API, there was no documentation. So you're basically just curling endpoints and hoping for the best. And the documentation was all incorrect. And if you want to see my personal feelings about the original implementation of that, if you can go to the Twitter community website and just look for my name. That said, it is much better now, and it does actually work, which is important because they have deprecated the user streams API, which is how people did this previously. So there are a ton of Twitter bots that aren't maintained that are going to disappear in probably the August timeframe as that user streams and other streams API goes away. So the account activity API works by taking a webhook. And a webhook is just this concept of this HTTPS endpoint that you host, that you are listening for connections on, and Twitter is posting stuff to that webhook. and it's secured. Now, the way that it's secured is outlined in the guide here. So this securing webhooks. What Twitter will do is when you first subscribe your webhook to the info or to the API, it will send a CRC to, or a challenge response check to the Lambda function. And the original requirement here was that you had to respond in less than 1 second, which was not great for Lambdas that were coming from a cold start. So I used to have to say, when you were starting all of this, you needed to test the Lambda function and get it pre-warmed. Luckily, that's not really necessary anymore, because 3 seconds, I haven't had a cold start in a Python function over 3 seconds in a very long time. So, and then Blasphemous says, if you want to do a portion of a session on webhooks with Splunk, you will be my personal hero. We actually have a Splunk integration into Kinesis now, which is pretty darn cool. I talked about that at reInvent last year. If you're interested in learning more about that, you can check it out on our YouTube channel. Just look at the live coding session. And will the VOD be available for this? Yes, it absolutely will. So, okay, let's look back at how we secure these things. I'm going to walk through this very, very quickly. So first of all, we basically take the consumer secret, combine that with the CRC that we got as part of the GET request. It's an HTTP capital GET request. And then we SHA-256 encode it. And then we return that SHA-256 encoded check to the requesting endpoint. And if we return this correctly, if we have the correct key and Twitter has the correct key, we're basically saying that this is all solid. This is all good. We agree that, I trust you, you trust me. And this prevents a number of different kinds of attacks. But it's not enough to do that just when you initially create the webhook. You actually need to do this on every single incoming request. So you have this verify request section. FGUID says test 1 2 3. Yes, we can see your text. So we verify this request by taking the Twitter webhook signature, which is again just another CRC based on the body of the message. And the downside of this being based on the body of the message instead of the downside of this being based on the body of the message instead of the headers is that if it were based solely on the headers, we would actually be able to do the authorization and verification entirely within the API gateway, because we could have a velocity template running in the API gateway that would go and calculate all of this stuff for us. But that's not the case, so instead we need to look at the whole request. Not a big deal though. So then we kind of base64 encode that, and we return whether or not the calculated HMAC matches the CRC that we got from Twitter. And if it does, then we know that we're good to go. So then we get down here, and if the path isn't right, then we just, we return a 404. But if the path is right and it's a GET request, then we know that we need to do the CRC check. And this was all kind of live coded in the previous session. So it's not the prettiest code in the world, but it was working. So if it's working, that's the first step. You spend typically the next few iterations making it good. So I would not describe this current series of conditions and kind of weird exception handling as good. I just describe it as working. So then we verify the request, and if the request is valid, then or if the request is invalid, so if the error code that we get from is valid request is over 400 or equal to 400, then we want to just return that response. Otherwise, we want to load the body as a dictionary, and then for each event in that dictionary, we want to print it. But what we really want to do is that we want to call out to SageMaker, and we want to say invoke endpoint, and I can actually do this from a sorry, I'm just gonna open this. I have this running already in a Jupyter notebook rather than trying to do it over here in this Lambda function. Let me just show you briefly. Oh, I don't know why my machine is running so slowly. This is infuriating. How do I? Wow, why is it going so slow? This is definitely the result of too little coffee for my machine. So something is definitely taking a lot of. So let's see. Yeah. OBS is unhappy. I don't know why it's taking so much of the CPU. That's abnormal. It's typically hovering around 10 to 20% of my CPU. So I guess it's just unhappy today. But anyway, we can proceed. We can make steady progress. And if we go look at the wow, sorry, it's just so slow. My computer is like 6 years old, so that would have something to do with it too. So we can look at the way this webhook is designed. So you can see here what I'm doing is I just have a proxy invocation and API gateway going out to this Lambda function over here, this WhereML invoker, which is the one that we were just looking at, and then we're bringing it back and we're sending it back to the client, and we can test it and we can say, hey, I want to run a Git, and it'll tell me that the CRC is invalid because I'm not posting a CRC. So CRC not provided or invalid. But Twitter, of course, would provide one, and since we have the correct credentials, it would be all set. So let's hop over. I can't remember which of these untitled notebooks I put the actual stuff in. And your boy Kizzle, I'm going to cover that SageMaker invoke code right now. Okay, so let's take a look here. And all we really need to do right now is create this SageMaker client. Now, because SageMaker has an API for instantiating the various endpoints, there are actually two different SageMaker kind of clients that you can create within the SDK. You can do runtime.SageMaker or just plain SageMaker. And just plain SageMaker are the APIs for standing up different containers and production variants and A/B testing models and starting new training jobs and all that good stuff. But the runtime.SageMaker is solely for invoking the endpoint. So we know that our endpoint is predict v2 and we've got a URL. In fact, if you guys want, we can go and talk about using another URL. So let's what's an image? What's a unique location that you guys would like to test? Any location at all? I need some more water. So I'm gonna let you guys type in the chat for a second. Try and come up with a new location. Aruba, Indonesia. Let's go with something. So Indonesia and Aruba and everything. Those are very large, broad places. Jamaica. Oh, Aruba, Jamaica. Yeah, let's go with something obscure. Lockjaw, Kentucky. That's pretty obscure. Never even heard of that place. Sydney. I'm still waiting for something unique. Remote island. The problem is I'm not going to know where this is. So I guess I could take these latitude and longitude coordinates that RLS Malay just posted. Go to Google Maps, drop a Street View pin, and then see what happens. So I can go drop the Street View over here. Good old super slow internet. I have been around here before. This place looks so familiar. Oh, this is Apple's HQ. Okay, so we're just gonna take a picture. I'm gonna take a screenshot of this location. And then I'm gonna put that on S3 really fast. If you guys come up with somewhere else too, and if you DM me an image URL and I open it on another screen and it is appropriate, I will test the network with that as well. And please, no comments on the number of S3 buckets that I have, which is a lot. Wow, it's so slow. It's not AWS though. It is just my potato computer. We're gonna upload that screenshot I just took. We're gonna make it publicly readable. Upload. I could have done this probably through. I'm sorry guys, you can't post the links directly in the chat. You can DM me though. And that shouldn't work. I'm unbanning the people who posted them directly in the chat. Sorry. So I've got this now. Copy link address. So we're going to take this image, and we're going to paste it in, and we're just going to say, give me the top 3. And of course it doesn't work. What is the error here? Some sort of TLS handshake error. Huh. That's weird. Haven't ever had to deal with that before. Yeah, it's really weird. You know what it is? It's probably an SNI thing. Server name identification. Handshake failure. Interesting. Let's just go to Google Images and find some stuff. And then in 5 minutes, I'm going to go on vacation. So, what's a weird random place? Roswell, New Mexico. I'm trying to find something that's fairly obscure because all these signs are pretty accurate. This one looks super random and it's small. Let's go with something a little bit bigger. Yeah. TripAdvisor.com. Let's use this image. Copy image address. We'll throw this in. And these are the coordinates we got back. We can map those. And hopefully it's in Roswell, New Mexico. And if it's not, I'm going to give up and go to sleep. Come on, slow internet. Slow computer. It doesn't ever normally go this slowly. Huh. Jeez. You know, it's almost faster to just do it all locally at this point. Like, I feel like everything is just okay. So here are the coordinates. I'll paste them in the chat. Someone who has working computer could probably tell me if they're right or not. So we're looking for Roswell, New Mexico. No, what my computer needs is less of the insanity that's running on it from our corporate IT and more of the RAM dedicated to like actually running useful stuff. So Oklahoma City is not right. What about the second one? Let's go with 10. Arizona is pretty close to Roswell. So, if you really want to, see this in action, you can test it yourself. Just go to twitter.com/whereml and you post a picture. You can post something from your camera roll. It can be indoors, outdoors, doesn't really matter. And oh man, this is just unbelievably slow and bad. And it'll tell you where in the world it thinks it is. It'll get it exactly right sometimes, and it'll get it completely wrong sometimes. It's really just based on the data that we have and how things work. So thank you guys for joining in today. That's really all I'm going to show. I'll post some links now with all of the different content. So if you want to see most of the code, if you want to see the slides, if you want to see Twitter, then go ahead, try it out. I do use the images that are posted to retrain the network, but none of your information is associated with any of that. So it's just, it's not tied to you in any way. I am going to go to bed. And I want to say thanks everybody who joined the AWS Innovate conference today. I hope you enjoyed the other sessions. If you want a session with me with a little bit more rest, try the first one we did earlier today. And thanks again. Hope you guys all have a good day. I'm trying to start I've been trying to click stop streaming now for like a minute, and I'm just gonna keep talking until it actually stops streaming. Oh my god, this computer's so slow.